Hello everyone, I'm Sihang. I'm a PhD student from the Bendable Electronics and Sensing Technologies group at the University of Glasgow in the UK. Today I'll be presenting a highly sensitive flexible capacitive pressure sensor with zinc oxide nanowire interlayers. Thanks to Dr. Yogi Kumaresan and Oliver Ozioko and Professor Ravinder Dahiya for their contribution of this work. In this presentation, I'll be introducing the motivation of this work, fabrication processes of the capacitive pressure sensor with zinc oxide nanowire interlayers, the experimental results regarding the sensing performances, and the conclusion. Now I'll be starting with the motivation of this work. The motivation of this work originally came from human skin. As you can see from the image, where there are various mechanoreceptors that sense the external stimuli by using different sensory receptors at different depths inside the soft tissue. For example, the Marco cells and Meissner corpuscles are closer to the surface for light touch sensation. The Ruffini corpuscles are further away from the surface for sustained pressure. Inspired by these, the electronic skin has become a trending topic which has been used to mimic the transduction mechanisms of the human skin with a network of flexible and stretchable sensors. A wide range of e-skin applications has gained a great amount of interest, such as wearables, prosthetics or robotics, health monitoring, touch panels, etc. And one thing that has been shared by all these applications is flexible pressure sensors. In this work, we focused on the capacitive pressure sensors because of their simple fabrication, low cost, high sensitivity, and remarkable environmental stability. The most common structure of capacitive pressure sensors is a dielectric sensing material sandwiched between two conductive metal layers. And the sensitivity of these devices is highly dependent on the materials of a dielectric layer. In order to improve the sensitivity, 3 different fabrication techniques are usually adopted. The first one includes the introduction of microstructures such as pyramids, pillars, or wrinkles. The first image at the bottom shows an example of using double-sided nanopillars. The second one uses nanofiber dielectric materials with porous structures, as you can see from the middle image at the bottom. The third one is to develop composite dielectric materials by introducing filler materials such as carbon nanotubes, silver nanowires, etc., which is shown by the bottom right image as an example. And in this work, we adopted a new fabrication approach to improve the sensitivity of the capacitive pressure sensors. Now I'll be introducing the fabrication processes on the following slide. We fabricated 2 PDMS-based capacitive pressure sensors with and without zinc oxide nanowire interlayers. The reason why we chose to use PDMS was because of its good thermal and chemical stability, effective dielectric property, biocompatibility, and excellent mechanical property to undergo a reversible deformation. At the start of the fabrication process, the top and bottom electrodes were prepared by depositing titanium gold on a PVC sheet. For the PDMS-only based sample, we spin-coated PDMS on an electrode, then placed another top electrode over it, while the PDMS was still semi-cured to ensure a firm adhesion. For the sample with zinc oxide nanowire interlayers, we firstly drop casted zinc oxide nanowires on one electrode, then spin-coated PDMS after annealing zinc oxide nanowires. Then we placed another electrode with drop-casted zinc oxide nanowires on top of the half-cured PDMS. And now I'll be moving on to the experimental results of the two samples regarding their sensing performances. We evaluated the sensing properties by measuring the relative change in capacitance at different pressure ranges up to 50 kilopascals. The standard PDMS-based capacitive pressure sensors revealed a relative change in capacitance of less than 7%. On the other hand, the sample with zinc oxide nanowire interlayers had that of almost 100% for the same pressure range. And from these results, we extracted their sensitivity at different pressure ranges, which are 1 to 10, 10 to 20, 20 to 50 kilopascals. The sample with zinc oxide nanowire interlayers showed a higher sensitivity for all pressure ranges, especially at the low range from 1 to 10 kilopascal, with an improvement of about 50 times higher than the standard PDMS sample. So the addition of zinc oxide nanowire layers has clearly played an important role to improve the sensitivity. And this enhancement in sensing performance is attributed to the piezoelectric effects of the zinc oxide nanowire interlayers. To take advantage of the piezoelectric effects, during fabrication, we placed the zinc oxide nanowire layers closely next to the electrodes to enhance the electrical connection from the electrodes to the dielectric material. And under the influence of a vertical pressure, the drop-casted zinc oxide nanowires become polarized and more compact. At the same time, the introduced charge carriers are generated because of the polarization effect. Then it sequentially interacts with PDMS and therefore strengthens its dielectric property. After studying the sensitivity, we also assessed the two samples' reliability by carrying out a cyclic loading test by loading and unloading the sample using 1 Newton force at a frequency of 0.33 Hz. As you can see, the sample with zinc oxide nanowire interlayers on the right-hand side shows a full recovery response, less noise, and a larger range of capacitance change by a factor of around 21%, which indicates a higher stability and reliability compared with the PDMS-based capacitive pressure sensor. In conclusion of this work, we fabricated two PDMS-based capacitive pressure sensors with and without zinc oxide nanowires. Then we evaluated the sensing performances and observed that the electrical connection from the metal to PDMS could be reinforced by introducing zinc oxide nanowire interlayers. By taking advantage of zinc oxide piezoelectric properties, the device performance was enhanced by zinc oxide nanowire interlayers with 50 times improvement in sensitivity at a low pressure range, which was 1 to 10 kilopascals. Currently, we drop-casted the zinc oxide nanowires, which were distributed randomly. So we're planning on further investigating the device performance by studying the effect of zinc oxide nanowires alignment in our future work. At the end, I'd like to acknowledge all the funders for their generous support: PH Coding, EPSRC, the University of Glasgow, and the James Wood Nanofabrication Center. Thank you everyone for your attention, and thank you everyone from the BEST group. It's been a great pleasure to have been able to take a part in this conference. Feel free to follow our group on social channels for more information.